What I want to do now is collect a bunch of rules for calculating determinants. I'm calling it properties of determinants. Some are going to be completely trivial, like the first one I'm going to write. Others may require, even to believe them, require some thinking, but we're not going to do a lot of proofs here. We're just really listing them. It's like a big shopping list of rules. Okay? So here's the first property, and this, you should agree, is obvious. If one of the rows or columns is all zeros, then what is the determinant?
0.
Right. Then the determinant is 0. Because choose that row or that column, which is all zeros, and use that. So you're going to have 0 times a minor, minus 0 times a minor, plus 0 times a minor, minus 0 times a minor. Obviously, it's just going to be all zeros. So this is a trivial statement once you know that you can develop the determinant using any row or any column. Good? So I'm even going to skip giving you an example. This is really straightforward. Okay? Property number 2. The determinant of triangular matrix is the product of the main diagonal entries. I'm going to convince you that this is true using an example. Okay, so let's take a 4 by 4 triangular matrix. Here's a triangular matrix. A triangular matrix can either be upper triangular, where all the entries above the main diagonal are non-zero, or lower triangular, where all the entries below the main diagonal are non-zero. So this is going to be a lower triangular matrix. 2, negative 3, 0, 0, 4, negative 1, 3, 0, and 2, negative 5, 1, 2. How do I find the determinant? How do I calculate it? I have to choose a row and choose a column. Let's choose the first row. All of these contribute nothing, so the determinant is just 1 times the corresponding minor. The corresponding minor is cross out this row and this column, you get left with this. Negative 3, 0, 0. Negative 1, 3, 0. And negative 5, 1, 2. Good? Again, I have to choose a row or a column. I'm not going to be at all creative. I'm going to choose this. What do I get? I get these two contribute nothing. I just get negative 3. Let me write this as 1 times negative 3 times this minor. 3, 0, 1, 2. That's it. And this is just 3 times 2 minus 0 times 1. So I get 1 times negative 3 times 3 times 2. You can calculate this number. It happens to be, what, 6 times negative 3, negative 18. But that's not what I care about. What I care about is that it's just the product of the main diagonal entries. Good? Okay, and the proof of this statement would be precisely writing this abstractly. A11, A12, A13, A14, up to A1M. A21, A22, and doing this exact thing. You can see that it's tedious, but there's nothing to it. There's no further theorem to use or anything bright to say. It's just what we did in the example to spell it out abstractly in general. Okay, next. So this was property number 2. Property number 3. If we exchange 2 rows or 2 columns, in doing row operations, exchanging 2 rows was a legitimate row operation, meaning that, for example, the 2 matrices had the same null space, represented the same set of solutions, okay, for a system. When you exchange 2 rows in a matrix, it doesn't preserve the determinant. The determinant changes, but not too significantly, only by a sign, okay? So if we exchange 2 rows, the sign, only the sign of the determinant changes. So if the determinant was -5, you change 2 rows, the determinant is going to be 5. Okay?
So if we do it twice, we just get the same result.
Right. If you do it twice, it's like doing nothing. Okay? So example, let's take this matrix. I'm taking purposely something very easy. Okay? So the determinant here is 1. I can see it right away because it's a triangular matrix, so it's the product of the diagonal entries. Let's change 2 rows. Let's change, for example, what did I change? The first row and the second row. So 0, 1, 0, 1, 0, 0, and 0, 0, 1. Okay, I switched 2 rows. What's the determinant now? Well, I have to choose how to evaluate it. Let's evaluate it, for example, using column number 2. Any choice would be good here because there are plenty of zeros all over the place. So what do we get? It's 1 times 1, 0, 0, 1, but it's an even column, so we start with a minus. Good? So the sign flipped when we exchanged locations of 2 rows. Number 4, if A has 2 equal rows or columns, then the determinant of A is necessarily 0. Why is that true? Why is that true? Suppose you have, I'm justifying it, I'm not going to write it, but here's the idea. Suppose there are 2 equal rows, okay? The determinant is something. Let's call that something S for something. The determinant is something. When I exchange the 2 rows, the determinant is going to become minus whatever it was, because the sign changed by 3. So like this, the determinant was S. Now the determinant is minus S, but these were equal rows. It's the same matrix. So for the same matrix, the determinant is S and minus S simultaneously. That can only happen if S is 0. Do you agree? Okay. So idea of proof: exchange the 2 rows, the 2 equal rows, by 3, you would get that A equals minus A. Right? But this equality, a number equals its negative, if and only if that number happened to be 0.
Can we prove it by...
This is the idea of the proof. It's everything, okay? You need to, in fact, it's a proof. It's really the proof.
Doesn't it suffice to say there's a row of zeros?
No, there isn't. If it has two equals rows, doesn't mean there's a row of zeros. All I'm saying is that two rows are the same. Okay? Okay, property number 5. A common factor of a row or a column can be taken out of the determinant. What do I mean by this? Let's do an example. Let's look at the matrix 1, 2, 3, 8, 10, 12, 7, 8, 9.
Divide them in the row by 2.
Well, be careful with the word divide. Do you see that row number 2 has a common factor of 2? Okay, this is 2 times 4, this is 2 times 5, and this is 2 times 6. Okay, so this equals 2, which I pulled out as a common factor from the second row, times the determinant of 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? And we know that this is 0, therefore this is 2 times 0, which is 0. This is because we calculated this determinant earlier, and we saw that it was 0. Okay, so that's what I mean by a common factor of a row or a column can be taken out or pulled out of the determinant. Okay? Again, this is different than row operations. Okay, in row operations, multiplying a row by a scalar didn't change the system, for example. Here it does. A scalar shows up. Okay, here the determinant was something. The determinant of this is 2 times the something. Okay? Word of caution. We had advice, now we have word of caution. Suppose we have alpha A, alpha C, B, and D. The determinant of this thing, you can pull out the alpha, right? So it's alpha A, B, C, D. I pulled out a common factor out of the first row, right? What is the word of caution? What is the word of caution? The scalar here that was pulled out of the determinant didn't multiply all the entries, like when we multiply a matrix by a scalar. It only multiplied one row or one column. Okay? So it's not true. This is true. So in general, if we take a matrix A and multiply it by a scalar alpha, multiplying a matrix by a scalar is multiplying every single entry by that alpha. This is not the same, or let's write what it is the same. It is the same as you'd have this alpha in every row and in every column. So you would pull it out how many times? N times, 1 from each row. So this is the same as alpha to the power n times the determinant of A. And it is not the same, and alpha A is not the same as alpha A. That's the point. Okay, so scalars do not just hop out of determinants, they hop out with the power n if they're on every entry. Okay, and they hop out once if they're only in one column. Okay, so this is the word of caution. This you can call a property. Okay, so this is in fact a property that follows from number 5. Good? Clear? Okay. By the way, why is this true? This is pretty easy to convince yourself that it's true. Suppose we were to evaluate using this row. We would get precisely 2 times the minor times 4. 2 times the minor times 5. 2 times the minor times 6. We would get precisely 2 times the determinant of this. Do you see that? Do you see why this is true? Okay, if we were to evaluate using exactly this row, it's completely obvious that this is what we would get. Okay, and that's the way a general proof would go. Okay, clear? Okay, where are we? Number 6, property number 6. If one row or column is a multiple of another row or column, but respectively. So if one row is a multiple of another row, or one column is a multiply of another column, then the determinant is 0. Oh, this is another way of denoting the determinant. I didn't mention it. Okay, I used only the vertical bar notation. This is an equivalent way of denoting the determinant. You'll see this in many books or people use it. And okay, good. Happened by mistake, but it's good that it happened. Okay, so why is this true? So if one row is a multiple of another row,
take out the scalar
right, take out the scalar multiple. You'd be left with 2 equal rows. And when there are 2 equal rows, we know that the determinant is 0. Do you agree? Okay, so idea, take out the scalar be left with equal rows. Okay, this is very informal, but that's the idea. Good? Clear? Everybody? Okay. More properties. There we are. 7. If we add, so note that we are discussing those row operations. We had in property number 3, we had the row operation of exchanging rows. In property number 5, we had the row operation of multiplying by a scalar. And now, what is the next one? Add a scalar multiple of one row to another. Okay, so if we add a scalar multiple of a row or a column to another row or column, then the determinant doesn't change. So this is in fact an operation which the determinant doesn't sense. It's invariant. Okay, so let's see an example. I need a new board. In fact, I need a new marker. This one is pretty much dead. Let's go here. So here's an example. 1, 2, 3, 4, 5, 6, 7, 8, 9. So let's add to row 1, row 2, and row 3. So what I'm doing is R1, I'm replacing it by R1 plus R2 plus R3. Do you agree that that's adding scalar multiples of rows one to another? Okay, so what do I get? I get 12. Tell me if my calculations are correct. 12, 15, 18, 4, 5, 6, and 7, 8, 9. Do you agree? Okay. And now observe that row 1 is 3 times row 2.
0.
Therefore, the determinant is 0. Right? If one row, that was property, what? Property 6. If one row is a multiple of another row, then the determinant is 0. Right? Because we can pull the 3 out and we have 2 equal rows. Good? Okay, so this is just an example of this property, of this fact. I want to show you another example. Here's another example of using these facts that we accumulated to do calculations. And the point is that all these little things are little tricks, little things you can do to simplify calculations. You don't need to calculate all these enormously many minors every time. If you can observe any one of these facts or do these little operations and just pay attention to what you're doing, right? If you're pulling out a scalar, you have to remember that the scalar is there. It does change the determinant. Okay, if you switch 2 rows, that's fine as long as you remember to put a minus sign. Okay, so here's an example. Most of our examples so far were over the field of real numbers. Let's do a complex example, okay, to maintain the flavor. So here, 1 plus I, 1, 1, 1. Let me erase this, it's in the way. Let's erase everything. I'm going to need some space for this, so let's just write it here. So it's going to be a 4 by 4 example. 1 plus I, 1, 1, 1. 1, 1 minus I, 1, 1. 1, 1, 1 plus I, 1. And 1, 1, 1, 1 minus I. So there are no zeros here. So it wouldn't be that wise to just start evaluating because you'd have 4 3 by 3 minors and it would be a lot of calculations. Okay? But what we could do is take R1 and replace it by R1 minus R2 plus R3 minus R4. Okay? We know that doing these things doesn't change the determinant. This is adding multiples of other rows doesn't change the determinant. So this is an equal sign. And what do we get? So 1 plus I minus 1 is I, plus 1 minus 1. So we just get I. Do you agree? And now I'm not going to do all the calculations. You can check me out. So what you get is I. Take the, sorry. 1, 1 minus I, 1, 1, 1, 1, 1 plus I, 1, and 1, 1, 1, 1 minus I. Now I can pull out an I, right? There's a common factor in this row. I can pull it out. Remember, there's an I here. And I'm left with 1, 1, 1, 1, 1, 1 minus I, 1, 1, 1, 1, 1 plus I. It looks like this is going to take a while, right? We didn't... What happened? Only this one changed, this 1 plus I changed to a 1. It looks like nothing much happened so far. But in fact, we're very close to wrapping this up. Now, subtract the first row from all the rows. Okay? So R2 is going to be R2 minus R1. Again, these are operations that don't change the determinant, right? And we get this I that already lived outside here. 1, 1, 1, 1. And then we get plenty of zeros. 0, minus I, 0, 0, 0, 0, I, 0, 0, 0, 0, negative I. Now it's a triangular matrix. The determinant is the product of the diagonal entries. So I get I that lived out here times 1 times minus I times minus I. So 1 times minus I is minus I, times I is minus I squared, which is minus minus 1, which is 1, times minus I. So it's I times minus I, and this is again just 1. And we're done. Good? Okay, so here's an example of a calculation that could be tedious if you were to calculate plenty of 3 by 3 determinants here, 4 of them, all with complex numbers, and then these would start multiplying and the expressions would get kind of, and if you try fooling around with it and try things, it's really a trial and error sort of approach. You can often save yourselves a lot of work. Okay, so I want to mention two things, and then we'll have to end, and we'll continue with determinants in a separate lesson. We still have some stuff to say about them, but just 2 more remarks. So, remarks. 1, if we do row operations, the determinant changes. That's a common mistake, to do row operations and claim that the determinant remains the same. That's not true. Okay? It doesn't change greatly, but you must pay attention to plus minuses that occur when you interchange 2 rows or 2 columns, and scalars, which come out of every single row or column in which they are a common factor. Okay, so it's not true that row operations or column operations do not change the determinant. It does change by these. So that's the first comment that I wanted to make. But if A and B are row equivalent, the first comment was they don't have the same determinant. They don't have necessarily the same determinant, but the determinant of A is 0 if and only if the determinant of B is 0. And this is going to be a very useful fact later. So the determinant itself is not an invariant, but being 0 is. Why? Because if the determinant of A is 0, okay, all these operations, plus or minusing 0, would not change it, would keep it a 0. And pulling out scalars would not change it, because you'd get 5 times 0, times 7 times 0, times whatever. So these row operations, which is what you do to transfer from A to B using row operations, one of them doesn't change the determinant at all. That's adding scalar multiples of a row. And the other 2 only pull out scalars or change the sign. But doing that to 0 does not affect it. Okay? So pulling out scalars multiplicatively does not affect the 0. Is this clear? Okay? So this is going to be a very useful fact. I would actually call it a theorem. Okay? But I wrote it as just a remark. Two-row equivalent matrices do not have the same determinant. But if one is 0, then so is the other. Okay? Good? Okay. So we'll stop at this point, and where we're heading, what we want to discuss next, there are some more properties that I have to mention. For example, what is the determinant of a product? We didn't say that. Okay, and there are some more properties. And in particular, we want to look more carefully at the relation of determinants to inverse matrices. Okay, and let me just give a big spoiler. Remember that theorem with the 4 equivalent statements. So there's going to be a 5th one. A is invertible if and only if the determinant is not 0. Okay? And then we're going to see, using determinants, in fact, a method for solving equations, a different method. And in fact, yeah, but let's leave some stuff for next time. Okay, so we're stopping here.